So on Friday we did the net force problem, but we didn't get to example number 3. So let's have a look at this one here. Example number 3 says that a force of 50 newtons is applied to a 10 kilogram snow sled at 30 degrees above the horizontal. The force of friction present is 18 newtons, and we need to find Fh, which is the horizontal component, F net, and the acceleration. So when we talk about components, we're talking about this triangle here. This is Fh, and this is Fv. Yes, Quinn? Say again? No, Fh equals Fh. Fv is another thing. Fh is the horizontal component. How much of that 50 newtons is actually pulling it sideways? And the vertical component is how much of it is actually lifting it up. Okay? So what we have here is we have a right triangle, right? The horizontal component is adjacent, so it's simply going to be Fh is going to be F cos theta. That's pretty much entirely always true. The only time it isn't is when you're drawing the 30 degrees in relation to the vertical. So this is going to be 50 cos 30. 50 cos 30. Which is 43.3. So only 43.3 newtons is actually pulling it sideways. Okay. Now the net force, because we've got 18 newtons backwards here, the net force is the applied force plus the friction force. So that's going to be our 43.3, and then we're going to subtract 18 from that.
Question.
Yes, Quinn?
That's your Fh, what about Fa? What's that? Force applied.
Yeah, that's the overall applied force.
Pardon?
That's the overall applied force. 50 newtons is being pulled up at 30 degrees. Okay, I guess in this case it should be, you're right, in this case here it's the horizontal. Correct. Right? Yeah, you're right. And now to find the acceleration is simply going to be F net is equal to ma. The net force, 25.3. The mass of the sled was 10. So we divide by 10. 2.53 meters per second squared. So what I would normally do, because we didn't quite get as far as I wanted to on Friday, I would normally give you time to work on the net force problems there with Darth Vader on them. Okay, but I would like to talk about inclined planes as well today. Try to make up a little ground here. Okay, so we're going to move on to inclined planes. Before I do any notes here, I'm going to show you a little app that I found. Yes, Quinn. Yes, I noticed.
What about the pipe thing for the X in the circle?
Okay, so here we have the inclined plane. Now you'll notice here, you might remember, did we do any inclined planes in grade 11? I don't think we do, right? Okay, so let's just have a look here at the, reset that. When you change the angle down, you'll notice that the up force here, okay guys, I need you to focus, okay? You'll notice that the weight force and the normal force are equivalent and balanced to each other, right? Equal and opposite. But as I incline the plane, right, which one is the normal force? That's the normal force. Which one's the weight force? That's the weight force, right? Are they balanced? They are not. In fact, this right here, this bit here, is numerically equivalent to the normal force, or F perpendicular, right? It's equivalent to it. You'll notice that there's a little tiny one right here, okay, which I call FD. That's the force, Cody, that actually drags the block down the plane. Okay, this FD is a component of the weight force that is down the plane. And obviously, the bigger, why does it do that? The bigger the angle, the greater that little FD becomes. Watch as I increase the angle, right? See how much bigger it gets? Right? Now, does it make sense to you that the steeper the angle, the less the friction? Because we're more and more closer to like a free fall kind of thing, right? Okay, so let's just watch here what happens. I'm going to set it to, we'll go about a little less. We'll go about 20 degrees or so, and I'm going to press go. How come it doesn't move? I got too much friction, right? Let's pause that. Reset it. Let's move my static friction down a little bit. Still too much friction. There we go. Now you'll notice, what did you see? They've got, I can see vectors, I can see velocity in blue, acceleration in red, and the force is in green, right? I'm just going to reset that. Right now, all I see is the force vectors, right? But once I run it, what happened to the blue vector as it went down the ramp? It got bigger because it's going faster and faster. What about the red one? What happened to it? Should remain the same. How come? And it remains constant, right? The acceleration is dependent upon the angle of the ramp. So we can play along with that kind of thing if we want. Okay. So I would like you to draw that picture. You should write as your title, your heading, motion down an inclined plane. That's just a picture there to remind me to go and look at that app, that's all. So write down motion down an inclined plane. Okay, so what we've got here is we've got a ramp. We've got a box up here, and then these are certain vectors, which I am going to label. Now down here, I'm going to put an angle theta. Actually, I'll try a different color here. It might be easier to see. I'll put a theta right there. Okay. This one here, I'm going to label with FW. This one here. That one there is FW. That's the weight force, right? The weight of that block, gravity is pulling it straight down. Remember, of course, that FW is equal to m times g, mass times gravity. Okay? Now, does it make sense to you that what angle is here is the same angle that's right there? Yes. Like if this is less, then that's going to be less, right? It would be exactly the same. In fact, the triangle that's the ramp, this triangle here, would be similar to that triangle there. Similar meaning that it would have the same ratios, right? This is just a smaller version of that, right? So this is the same angle right here. Now this one here, I like to label FD. Okay, it's the component of the gravitational force that acts down the plane. That's why I use the letter D. Down the plane. Okay. Now there is another one here, which is actually equal to the normal force, right? The normal force is how much the table, this is the Stefan and Quinn force, right? This is how much the table pushes up on the block, right? Now, does the block move up this way? Like, does it accelerate that way? No, it doesn't. How come? Because there's a part of the gravity is pulling it down. So this one here, this is actually the component of gravity that is numerically equivalent to the normal force. This one here is the component of gravity that acts opposite to the normal force and is equal to the normal force. I like to call it the normal force. It's easier to say than the component of gravity that is numerically equivalent to the normal force. Thank you. So we'll call it the normal force. Okay? The only thing is that it's in the opposite direction. That's all. Okay. You could. Basically, that's what it is. Now, this FD I also like to sometimes put right here. Okay? These two are equivalent right here. I've just put it in a different spot. Okay? That's normally how I draw it. And I think that's about it. Yes, Quinn?
Can you just not draw the triangle at all? Just put the D up there and the F?
Yeah, yeah. I'm just showing you sort of where that all comes from. Yeah. Good point. Okay, so when an object sits on an inclined plane, gravity acts to pull it down the plane. We call that FD. And gravity also acts to push it against the plane perpendicular, FN. And you could say the quantities Fn and Fd are simply the components of the weight force. Okay? Now what we've sort of done here is, and if I could just go back to this, I know you guys are copying that. What I've done is I've sort of changed the axis. Instead of the axis being X and Y, right, I've sort of rotated the axis, and this is the component that is the old Y, right? And this is the component that's the old x, but I've just relabeled them, just sort of twisted, that's all. Okay, so it's a components idea. So the quantities Fn and Fd are simply the components of the weight force. Okay. So what we need to do is we need to figure out how do we determine what those components are equal to. So from that triangle right here, remembering that this is theta right here, and this is Fw, and this is Fd, and this is Fn. Well, clearly you can see that Fd is opposite the theta, right? So sine of theta is Fd over mg, or we can say Fd is mg sine theta. That's a new formula for it. Likewise, the normal force component is adjacent to the theta, and so cos theta is adjacent over opposite, or adjacent over hypotenuse. So I get Fn over mg, or Fn equals mg cos theta. Those are two things you now need to know. Okay, so let's try out these new formulas. Let's take them for a bit of a test drive. We're going to put a 5 kilogram box on a 30-degree ramp. We're going to put it 1 meter up the ramp. And I want you to find Fw, Fn, Fd, A net, time to get to the bottom, and the velocity to the bottom. Lots of things to find.
This isn't up in the sample, right? No.
This is sample number 1. Here. On a frictionless surface, F net is equal to Fd, right? Because you've got your box like this, right? Fd is down. There's no friction to oppose it, right? So, what does that mean? I think I've got my notes a little bit backwards here. It means that if F net is equal to Fd, then mass times acceleration is equal to mg sine theta. And guess what? A is g sine theta. Only true, though, when it is frictionless. Only true when it's frictionless. Now, we are going to go through those different points there. Let me just see, what did I do here? I think I've skipped something here. I got to fix this. Does that make sense, though, why the A is equal to g sine theta?
Yes.
Now, do you remember when we tried to find gravity in grade 11 and we weren't very successful in getting 9.8? Do you remember doing that? And that was because we used G was equal to, on our graph, we found G was G was the slope of the A over sine theta graph. That's why we did that. We found the slope of, we graphed A and sine theta. We found the slope of it, and I said it should have been equal to G. How come it didn't work? Because it's not frictionless. It's only true on a frictionless surface. Okay? Some of you might have tried it on this ramp, and I think we got a better value, right? But it only works when there's no friction. Yep. Are you ready to see the answer? No? You want to try it? Okay, you guys give it a try. Okay, so very first thing we're going to find is the weight force. Mass times gravity. 5 times 9.8, which is 49 newtons. So we have 49 newtons, Mary, of weight force. Part B asks for the normal force. Normal force is mg cos theta. So that's simply going to be 49 cos 30, or 42.4. The next one asks for the force down the plane. That's mg sine theta, which is going to be 49 sine 30, or 24.5. Now, when you're doing inclined plane problems, you need to start with doing those three. That's sort of the things you have to do to start. Okay, it's automatic.
Is there a question on this friction? Would you say this like a friction?
Yeah, there's no friction here, right? There would have to be some, yeah. Yep. Yep. So at this point here, that's right. At this point here, if there was any friction, then you would get something like F net is equal to FD plus FF, and you would simply subtract the friction. Okay, but in this case there isn't. So I'll just add another page here. So now to find the acceleration, F net is equal to MA. So I get 24.5 is equal to 5A. I guess technically over here I should have said F net is simply equal to FD, right? In this case, because there's no friction, 24.5. So I get an acceleration of 4.9 meters per second squared.
I could have just used a, like,
You could have, yeah, you could have. But that only works when it's frictionless.
I mean, if it does the same thing with friction, we just.
Then you have to assume that it's, yep. Time to get to the bottom, I'm going to use D equals VIT plus 1/2 AT squared. The distance is 1 meter. The initial velocity was? 0. Plus 1/2 of... Now, should I use minus 4.9 here? Let's answer Mary's question here right here. She wanted to know about the negative. Now, technically, guys, can you just leave the spring for a minute? Technically, okay. Like, negative is down, right? But because everything is sort of twisted, some people might say, well, you know what, let's make down the ramp the negative and up the ramp the positive. You could do that, right? Like, basically, you're just assigning a direction to negative and to positive. You only need to worry about it when there are forces that are opposite. You certainly don't want to assign straight down to be negative, because then what does this become? Right? Like, it's not perpendicular, it's not anything. So yeah, that's why I said just leave the signs out for this particular one. Okay, so I've got my acceleration of 4.9 t squared, giving me a time to get to the bottom of 0.64 seconds. Is that what you got? 0.64 seconds. And the last question, what's the velocity at the bottom?
What's that?
Vf equals Vi plus At. So we've got 0 plus acceleration 4.9 times 0.64. The thing is traveling at 3.14 meters per second. Yeah, it's moving. Why is it moving so fast? It's a frictionless ramp. It's a frictionless ramp, and it's traveled a meter, right? And the angle was 30 degrees. Like, that's pretty steep. Right? Like, if I take this ramp and put it to 30 degrees, it's going to be going fast when it gets to the bottom, isn't it? We all know it's going to be going fast. Okay, so there's that bit there about g sine theta. There are some textbook questions that you can work on. There's this handout here. I would suggest you start with the handout first. They're a little bit easier. There's only 4. They're all relatively similar, so you certainly don't need to do all 4. The solutions, the answer on the back, and so is the QR code for the solutions. You should probably try some of those ones in the book as well. Okay? We're going to move into ramps with friction very soon.